this session?
Yes. Started.
And here we go. I would like to welcome you all to today's webinar on cognition aspects of collaborative VR-aided design environments as part of the PrismArch webinar series. Christian, the next slide, please. So we'll have a 5-part webinar today under the PrismArch label. First of all, I will be giving you a short introduction on why we are doing this under the label of From Cognition to Design and Virtual Reality. This will then be followed by a presentation on understanding cross-professional interaction and collaboration in AEC design by Martin Brösamle, followed by some inputs towards the development of UX design guidelines to support cognitive processes during collaborative design in VR by Panos Mavros and Martin Brösamle again. Some lessons learned from PrismArch prototyping and navigation experiments by Jiayan, Zhao. And last but not least, harnessing eye tracking to understand architects' visual attention during asynchronous collaboration by Vater. The next slide, please. So this is our team. Already heard how we are allocated to the various parts. We are a mix of cognitive scientists, psychologists, sports scientists, geographic information scientists, usability experts, and architects. And I leave it to you to guess who of us has what background. And skip to the next slide. So I will now talk about introductory words from cognition to design and virtual reality. And maybe a brief introduction about the background of our contribution to PrismArch coming from ETH Zurich. And some of us have now moved to other institutions. But this all comes out of the ETH Zurich Chair of Cognitive Science, which is active both in Zurich and in Singapore as part of the Singapore ETH Center. And our main mission is really to investigate human interaction with technical systems and spatial environments. And in the PrismArch context, of course, these two things converge. It's strongly about technology, but it's also very strongly about spatial environments and how they are designed in architecture, more generally in the AEC industry. And we really embrace an interdisciplinary perspective, and this is reflected in the team here. We're working a lot with designers, with architects and colleagues in computing and neuroscience. And as part of our Singapore activities, which complement the work here in PrismArch, we have 2 larger projects, one on cognition, perception, and behavior in urban environments, and then the architectural cognition and practice activities, which are just now going into their second phase, and which look at behavior in space rather than necessarily the design process per se. On the right-hand side, there's a link to a couple of current papers. In the interest of time, I'll skip that and go to the next slide, please. What is our research mission? There's very many ways of talking about this, but in the context of this presentation today, I would like to emphasize that we have a loop between cognitive science questions and architectural design questions. The cognitive science brings in aspects such as user needs and abilities, experiential factors, and a rigorous approach to behavior evaluation, while the architectural design provides access to elements such as design variations, to application and case studies, and a strong application-oriented view on challenges and problematics. Next, please. Furthermore, on the research mission, we very often look at things in this triangle of the architect, the building, and the users and their respective roles to one another with designing, anticipating, and using. And a lot of our work in architectural cognition then looks at understanding the users and informing architects by science as part of an evidence-based design practice. The next, please. And here I would emphasize that the work that we do at the interface with buildings and users is a large part of what we do in both the Singapore and the Zurich hubs. But for the time being today, next slide, we would emphasize, one back, please. I was still going to make that argument here, right? This pinkish background here. When the architect really, and thus the AEC industry, really moves into the focus of activity, then we look at technical solutions, like here with PrismArch, and the various roles of the architects getting informed by science, anticipating user needs, and designing buildings. Next slide. What is the context of this project and also of our contribution? The context is basically virtual reality, right? The upcoming transition of AEC processes into VR includes not only typical design activities like generating geometry and arranging geometry, but also extensive collaboration and co-design, review, and stakeholder engagement. Users will be a diverse set of actors, not only architects, with varying levels of expertise in design and virtual reality. And then we can ask, as psychologists, as cognitive scientists, as behavior scientists, questions about how do we design interfaces that support and empower users in such diverse design activities with diverse backgrounds. Next slide, please. And why would we look at this from a cognitive science perspective? We could also see this as a purely computer science or software engineering problem, but that would be falling short of some questions that we do raise. One is, how does design activity happen across different media? How do architects and engineers think about and of space? How can the interface support them to think about end users? So this is all about cognitive processes. How does design, collaboration, and interaction take place inside immersive virtual reality? What changes? How does a new interface influence users' cognitive load and attention? How can it support the spatial cognition, the sense making about space of complex environments in virtual reality for different user groups? These are genuinely cognitive perspectives. Next slide, please. And this also defines our role in the overall PrismArch project, and also in the 4 webinars that you are able to attend. And so we focus in our work packages on cognition aspects of collaborative virtual reality aided design environments. And this is the scope of what we're presenting today. Next slide, please. And this is organized for us in 3 work packages, which are again reflected in what we are sharing today as our outcomes and observations, looking at spatial cognition and navigability of large-scale spaces in virtual reality. We're looking at cognitive load and stress when one is immersed and interacts with complex visual displays. So this looks both at the spatial configurations that are being designed, but also at the complexity of the user interface. And this together leads to very practical and applied concerns about user experience and usability guidelines for designing interfaces in collaborative virtual reality aided design environments. The next slide, please. And with this introduction, it's my pleasure to now offer the stage to Martin Brösamle to present about understanding cross-professional interaction and collaboration in AEC design. Martin, the floor is yours.
Thank you, Christoph. You briefly mentioned in the introductory words the large diversity of next slide, please. of qualitative of design media and design activity, and that's also kind of the reason why I chose the theoretical perspective I chose for the early work in PrismArch, which was basically distributed cognition. So the idea is that multiple components interact to form a cognitive system that is composed of all these various interacting components. A typical example where this perspective has first been shown prominently in the literature and in the later discourse in cognitive science was the work by Edwin Hutchins, who studied cockpit and crew as one cognitive system that solves basically the task of navigating an airplane. And similarly, another study of him was to look at the navigation team instruments and basically the whole instrumentation in the ship, all working together as one cognitive system in a to solve the task of navigation, basically. Next, please. And that is kind of opposed to the typical perspective we tend to have when we think about technical systems and users interacting with them. We very often think that there's human cognition in one individual user, and this cognition this human cognition makes inputs to the technical system, and the technical system would produce some outputs to the user, who would then again do cognition about it. Next, please. The situation is rather more complex in the sense that there's multiple components all being involved in producing a cognitive system that makes sense and solves a task as a whole. Next, please. And in architectural design practice, we see this quite prominently in the sense that there's a large variety of design media, paper, digital software, tracing paper, and so on and so forth are all combined. And they are not simply used for offloading information that is basically too much to remember. They are actually actively involved in the task that people are trying to solve. So there's always an interaction going on between what the architect thinks might be a good idea, makes an early sketch on it, and it can be extremely vaguely with a wiggly line only showing a rough outline, and that would then again be visually processed and understood in a new way by looking at it, refining it, and so on and so forth. And I mean, this complexity is very much visible mostly in observation. You just look what architects do, like in the study by the group of Jennifer White. Next, please. Or in this case, studies I did, we again see unexpected ways in which media are combined. In the upper picture, you see somebody using a tracing paper in front of a computer screen in order to retrace some of the lines visible on the screen and develop the idea further on paper quickly, and then later re-enter it into the computer and stuff, and so on and so forth. That is, of course, interesting from a cognitive science and computational point of view, because the use of graphical media, as we see it in the analog or half analog office, architectural office today, is rich, it's robust, and media can be used in spontaneous and manifold ways, and also ways that we didn't anticipate properly. Next, please. So for PrismArch, this more or less means that we have a situation where we have a individual human thought interacting with physical media, information systems, and the task environment as a whole. And all that together plays together to solve a cognitive task. That is, as a theoretical background, I think very helpful for understanding these interactions. Next, please. So one of the activities we did early on in the PrismArch project was doing interviews with the people who from our partners who were involved in architectural design projects, and we asked them in particular about activities and tasks. What were the inputs for these tasks and activities? That would be images, documents, CAD files. And also what tools were involved. Was it a CAD software? Was it pencil and paper? Was it plan material? Was it virtual reality? How these were used. Next slide, please. And that brings in, or one of the prominent results from there is that there's a very strong timeline aspect, in the sense that documents get enriched and refined over the course of the project. And this enrichment process, next please, shows that these documents are more or less like collectors of information that are basically organizing the interaction of multiple people, and also, yeah, serve as a trace of who did what, and what information went in there, what information is also still missing. So it's extremely document heavy, which is also reflected probably in some of the other webinars about how documents get organized digitally in PrismArch now. This is not my focus too much today. Next, please. And the second point I want to make is that observing the behavior of people. In this case, it is a study run by Christian. We'll talk later about the study in more detail today, in how CAD software is used to basically not only stay in the realm of the physical analog design media, but also go into the digital. But again, has this character of being a medium in the sense that it is used in an unexpected way. And I will show some of these unexpected ways in the next slide. So the task people had here was to to check if all doors have the same height. And what we see is now 3 images. This is the CAD software in front of you, and you see the mouse pointer, and the bluish bubble you can see in the upper left view. Basically, the eye is the visual attention. It's the session has been eye tracked. What we see here, the person selects one door. Next, please. And then that door highlights in the other view, in the one to the right. Can you go back and forth once again, Christian? Here you see it. So the highlighting of this one door allows the user then to recognize where that door is located in the other view. Next, please. And we see this because the visual attention now goes to the right view and a zoom out occurs soon after that. So probably, Christian, you go back again to the first of these 3 images and we just click through them. So the door is still unselected, the door is selected, the attention goes to the other, and the view to the left is zoomed out simultaneously, by the way. So that's an extremely complex interaction you can see only in this short period of time. And I will not go into all of the details. I rather want to kind of make you aware of how fine-grained the interaction with this medium CAD software in this case is, and how careful you have to observe the interactions in order to fully understand what is in there. Next, please. So what we find is, or how we can describe this in a less video-intense way, is to identify micro-level cognitive strategies, in this case for inspecting CAD models, because the model was already given to the participants. And then we find interactions like hiding, obstructing elements. In this case, the ceiling covered most of the view. This is usually done via the layers dialog or by selecting the object and making it invisible temporarily. Task or the selection of tools in the CAD software is extremely task specific. For example, a clipping plane tool allows you to basically cut the entire model like a cake. In this case, this can be used to remove the obstruction of the side by the ceiling. And there was another task where angle measurement was involved, and there's also a specific tool for that. Next slide, please. So we have another pattern which is kind of related to the three images I showed in the beginning, which is that the mouse pointer rests in a certain position, and the eyes check other locations which are in the same view or in other views, and the mouse tends to be the point where the view returns to. So we have a similar behavior on paper and pencil, where one hand fixates one position and the other hand is showing, for example, to the client other elements that are important, but this one finger is maintained at the position where the architect wants to return to at a later point. And we see a similar pattern with the mouse pointer. Next, please. Yeah, exactly. The mouse pointer is used like a finger. I already said that. And yeah, in paper-based material, we have a similar thing. Next, please. So, and this is basically the protocol version or several protocol observation versions of what I showed with the images in the beginning. So I would probably just skip this one. And so an interpretation of that is that the coordination between the multiple views that we saw in the beginning, these 4 views, is visually complex, and that by selecting one of the objects, this object serves as an anchor, as a visual anchor that sticks out in all 4 views. And that is kind of, I mean, it's making use of the visual highlighting of selected objects, despite the fact that the selection mechanism was probably not intended to be used in that way when the software and the CAD software was designed. So again, we have this media-like interaction where the medium, or the tool in this case, is used in an unexpected way. Next slide, please. So here I come to my summary, which is basically that graphical media, and that explicitly means that it can also be digital graphical media, should be robust, they should be easy to grasp, they should be flexible in their application, all criteria that make them media-like and not just computer interaction, predefined. Yeah, I mean, the opposite would be a computer software in a way where like an input dialog to some very specific information on the web, where the designer has decided in each step, the user will make exactly these will provide these informations, and then is the next step, and so on and so forth. But here we have it, we deal with a medium that can in a way flexibly adapt and be used by the user for the task at hand, and it can be used in this way for very different tasks, and will be employed in a flexible way here. And that of course implies that from a computational view, these uses might be unexpected, and we have to be careful when designing design environments like the one in PrismArch, that we don't overlook important interactions that would later be needed and probably be difficult or impossible to achieve. That's why we are doing these studies. And so I close with the last sentence that qualitative observations can reveal the cognitive role of design media in design activities and team interaction, and hand over to basically Panos and myself. Well,
Thanks, Martin.
If there are questions, or do we do questions in the end? Probably in the end.
Are there any immediate questions?
If there's an immediate one, yeah. Okay.
You can also write your questions in the chat and we can pick them up later on. So in this third part of our presentation today, we would like to discuss our work towards the development of user experience design guidelines to support cognitive processes during collaborative design and virtual reality. And this was a work that really stemmed out of the research that Martin did in the first year of our work with PrismArch. So all of these qualitative observations in design studios with architects and engineers, but also in our internal testing of different design software, be it Rhinoceros, for example, or other newer software that we have access to in virtual reality. So we try to extract what is the general principles that would support a successful user experience in virtual reality. Next. So again, to reposition this in the broader context, the processes of design and collaboration across the architecture, engineering, construction industry require distributed cognition, as Martin was laying out. There are multiple actors. This can be the designer and sort of vertically within a single organization. So it could be a junior designer, a senior designer, or a partner in an office who have a say on a specific design. It could also traverse more horizontally the industry. For example, it could be a civil engineer working with a designer, or a mechanical engineer working with a civil engineer, but also outside kind of the world of engineering, there's also the clients, client services, and other parts of the profession that do have a say and are involved in this very complex task, which is to design the built environment. So the task performance, how well people engage in these design activities, and possibly also what is the outcome of that work, relies on the collaborative behavior, the interactions. And we do realize that the more there is new media coming into play, there can be increased cognitive load, depending on the individual, their expertise, the task they're dealing with, but also the system and the nature of that collaboration. Next. So our mission was to develop some initial user experience guidelines that could be used for the development of PrismArch, but also hopefully reflected more broadly in the research and software industry in the future. And we adopted 4 steps for this. We took a grounded theory approach, so we tried to really understand what is happening on the ground, as Martin outlined before. We also reviewed different software platforms, what is the state of the art today in terms of design. And we tried to synthesize both more theoretical ideas, also ideas that come from spatial cognition research or typical domain of work, and also the observations we made across the different media and tools. And with these, we try to extract general and generalizable principles instead of specific design solutions. So in the slides you will see afterwards, we don't have specific examples of how to create a menu, but we want to articulate that there should be a menu for a specific process. There should be an approach and an articulated design for different kinds of interactions with the software and with each other within virtual reality. Next, please. Martin, would you like to take this one?
Yeah, I mean, in principle, we divided the entire set of guidelines into sections so that it's easier to kind of digest them and also to structure. I mean, if you look at it in one of these sections, like general functionalities and requirements, or let's say section D, design specific requirements, I mean, they are all kind of linked between each other, and we try to introduce a lot of links between those guidelines. On the other hand, guideline is supposed to be something that is a concise statement that can be applied not uniform, but can be, is generic in a sense, that can be applied to different systems, that are also to systems that might occur in the future that we haven't thought of at that point. So when creating such a guideline, you try to, of course, be precise on what you have observed, but you cannot just type in it will be always like that, because in the next system it might be a complete different situation. So we try to abstract away from the specific context of the studies we did and still make it concrete enough so that the future reader will understand of, this is kind of the point of that thing. And especially when it comes to design, there are a couple of requirements, like the one that a medium has to be flexible in its application. I mean, yeah, that's nice to say, but what does it mean in practice, and how can a future developer apply this to his system? Is my system now flexible? How do I know this? And then, of course, they want this stamp saying, okay, yes, this system is flexible to use, and everybody's happy, but it's hard to come up with hard criteria to really do that. And that was kind of the situation of why we subdivided it in quite small statements, but made a lot of links between these sections. For that reason, we also introduced these letters, which will easier help you to basically navigate the guideline section as a whole. Next, please. Or maybe Panos, you wanted to.
Yeah, sure. So we basically developed approximately 80 guidelines or short statements, as Martin mentioned, which are all in the public domain. So you can consult the document that is publicly accessible. We have a link at the end of the presentation. And these can be grouped in these 6 general categories, and they cover things from, trust and the different user groups, how people interact with the UI, what kind of controllers and menus might exist, what are the principles that should guide their design, how different aspects that relate to collaboration, for example, how do we structure co-presence, but also how do we structure things like visibility of documents, privacy, access rights, and other less usually things that don't happen outside the digital domain. For example, taking notes or sketching on a piece of tracing paper. How can we bring these ideas back into a virtual reality software that encompasses all design activity? Thank you. Next slide. So we have extracted some of those guidelines. 80 guidelines are too many to run through in this short session, but we just want to give you a flavor of what these look like and some key dimensions that underpin our work. So in terms of general functionalities and requirements, we try to articulate, that a virtual space should be experienced in the way that it resembles or it's equivalent and comparable to our experience of physical space. Guideline 2, that the functionalities are of fundamental importance and general scope should be accessible at all times in some way or another within the interface that the user has easy access to. And these also relate to how people move in space. Further on, we think that there should be a seamless and continuous integration between immersive and desktop modes. This is how productivity work will happen in the near future between these 2 modes. PrismArch takes a very clear statement: all work should happen in virtual reality. So we try to imagine different scenarios of how this could play out. Next. Then there is other elements beyond the UI itself. How can we create a system that generates trust in the user, that sensitive content or important meetings between clients and architects, for example, and engineers will happen consistently. So there's elements that a designer of a system should consider in terms of how to make it, to implement it in a reliable way, but also how to have other systems and feedback loops that generate a sense of trust in the system that performs well and it's robust in different contexts. And there has been a lot of work from our colleagues. Some of them are now in the call, from Zhao and Sirth, on articulating what this idea of trust with different sphering levels, for example, can look like. So there's a general guideline about a principle and then a potential incarnation through the idea of sphering levels that you can hear in the next webinar. Next. We also looked on user groups and the fact that there will be different user groups. As we were saying before, there might be designers, engineers, clients, and other professions that are encountered in the design activity, and the system should be flexible enough to their needs and their capacities and their duties within that world, but also allow for customizability to each of those user groups. Next. Martin.
Okay. In terms of collaboration in VR, I mean, we very often encounter the situation that when people work on one task together, it would be important to have an understanding of where the other actors are, where their body positions are. I mean, stuff that usually works straight away in a meeting room, because you immediately understand, okay, we are on a table and there's a plan and we are designing here. And at the moment, I mean, there were huge discussions in PrismArch about scale. Is it possible that I work on a very small scale while somebody else is working on a larger scale, which immediately would mean that my avatar would be way smaller than the one of my colleague, and which could, in principle, operationally even make sense. But from a social point of view, we very straightforwardly realized that this would be just too silly to do. For example, your boss being a tiny avatar and hopping in front of you on the desk, while you, from his perspective, would be a huge person. I don't know, moving entire houses, where he was just repairing the furnishing of the door, for example. It's just not something that you want to have. And so the question is, of course, how do you create a situation where this simultaneous work on the same model is possible, while people are aware of those colleagues who they have to be aware of, but those who are probably working on a different scale should be doing this in a different virtual environment in a way, or in a way where co-presence is explicitly not possible. That raises, of course, also the question: in what tasks are we required to have asynchronous or synchronous communication, in the sense that we are all co-aware of what each other is doing, like in a meeting situation, or where it makes sense to really do this asynchronously. I'm making changes, then handing them over to somebody else. This other person making comments on my changes, and then I would review my or revise my changes again. At some point they get finalized. Next, I think.
So we also focused on spatial navigation and orientation, and we tried to really understand what is the difference between navigating and experiencing a space in virtual reality versus experiencing and navigating a space in a desktop setup, for example. So virtual reality is often argued that it's better for immersion, but also helps people have a better understanding of where they are in their surroundings. But at the same time, as Martin illustrated very briefly, and Christian will discuss in more detail, the kinds of interactions designers have with virtual space in a desktop mode is very different than just the typical walkthrough or the experience one has in game interactions in virtual reality. So we really spend a lot of thought trying to understand what are the differences and how a system should be able to support users in maintaining a good sense of where they are and where they're going, how they're moving through space, especially for the different user groups that might use a system like PrismArch. Next. For example, we looked on the idea of spatial desynchronization that Martin mentioned just now as part of asynchronous and asynchronous modes of collaborating. So, for example, people might be spatially desynchronized. They might be on the same virtual model, but working on different parts. You can imagine a football stadium where one person is working on the roof and another person in the same model in the virtual session is working on a different part of the building. But in other cases, we might want a system that allows the resynchronization where everyone has exactly the same viewpoint, for example, as part of a meeting or as part of a presentation to a client or the public. So different types of spatial interactions. Next.
Oh, yeah. Oh, Panos? No,
Yep.
before you go to the next, I mean, the typical situation in real world would be, okay, we are on a construction site and we are inspecting, for example, the electrical lines that have already been put, and where there have been errors in making these probably, or which parts are not yet finished, and so on and so forth. And we might be 4, 5, 6 people inspecting these, and one is the architect and somebody else is the electrical engineer, and so on and so forth. And they might all have their different perspectives on it, and they also might spread out and be distributed over the entire construction site, or in our case, the digital version of the future construction site. Then the question is, okay, now we have a situation where everybody has to look in one place at one particular item. How do we get them there? Do we port them out of the blue? So people might get disoriented because they suddenly are interrupted in the middle of their task, or do we ring a bell and say, like, in 5 minutes or in 5 seconds, we will be teleported to a certain location, and so on and so forth. So this is, as the guideline designers can only raise the awareness for that this problem might occur, and that we spotted it as a potential issue to be solved, but whether this future system will choose a bell or an immediate teleport or a visual flag in the view of the person, or a pointer of please be at this location on the map in 10 minutes and walk for yourself, is up to the designer of the system. We cannot solve this in the guide. Next.
On other parts of the guidelines, we also included these small snippets. They're featured in green, where we try to summarize ideas from the qualitative observations and the interviews in terms of, for example, how group activities take place in physical space. And here we're referring both to the design office. So how does 2 or 3 designers from different disciplines perhaps work together over floor plans and other representations of a project to identify issues or identify new solutions across the project stages. Project stages have very diverse types of activities, from ideation to conflict resolution or detection of clashes and geometries. But there is also social elements. There's hierarchies of more junior and more senior people within a team, different stakeholders that have a different amount of say on the decisions that are being made. So this captures this key idea that underlines the development of the guidelines. Next. So to summarize, we were starting to grapple with the idea of what are the cognitive dimensions of co-designing inside a virtual reality environment, where a coherent design session can take place. And with that, we focused on more how immersive virtual interfaces can support collaborative design activities. So we specifically tackled ideas of virtuality, immersion, spatial dimensions, but also the nature of collaboration, social structure, and design itself. With a grounded theory approach, we developed approximately 80 UX guidelines grouped in 6 families of design, spatial cognition, collaboration, interaction. If you're curious to know more about this, we have here the link where you can download the report, and you can, of course, reach us either immediately at the discussion or later on to discuss further. With that, it's time to move to the next part of our presentation, where Jiayan will introduce more about the UX prototyping and navigation experiments. Jiayan.
Okay. Yeah, thank you, Panos. And I asked for the remote control. Okay, good. Okay, so my talk will be divided into 2 parts. The first part is an empirical study investigating how people navigate, memorize, and develop mental representations of 3-dimensional architectural space. For example, a multi-level building. And the second part of my talk is about a series of user evaluations we performed using the PrismArch prototype, which I will not go into detail today, but just want to throw out a couple of interesting aspects, which I hope to discuss with you folks in the later discussion session of this webinar. Okay, so when people navigate in complex architectural environments, sometimes it can be very challenging for them to find their way to the destination. This is because in such a highly structured environment, the visibility from a single viewpoint can be very limited because of the existence of the walls, the ceiling, and the corridors. So consequently, the development of a coherent and integrated mental representation of the environment can be very computationally complex. But nowadays, we can use novel technologies such often through augmented and virtual realities to provide infinite possibilities to the visualization and manipulation of spatial information. So nowadays there have been many VR design tools that are either under research or have been released to the market in AEC industries. And one good example is the Akio. I'm not sure if I can play this video. Oh. Hello, Christian. Is there a way to play the video? Okay. So and one good example is the Akio, which is a collaborative design tool that allows users to easily sketch building models with others in the virtual reality. And one interesting feature of Akio, which has also been implemented in the PrismArch prototype, is the seamless transition from the building models on the tabletop to the surrounding of the users in a one-to-one scale. And from the cognitive perspective, the capacity to dissolve or shift between the local and the global characteristics of a architectural solution can synthesize the spatial information from many different locations and different sources, and therefore has the potential to overcome the limitations or challenges that people come across when navigating complex architectural environments. Okay, can we go back to the slides? Scroll down. Yeah, this one, just next one. Okay. So following this agenda, we performed an online study using Prolific. And the purpose is to identify environmental features that may cause flaws in individuals' mental representations of the environment. And based on the results, we also would like to provide evidence-based suggestions on the design of visualization techniques in virtual reality that hopefully can fill the gaps in individuals' cognitive maps. Next. Okay. And the virtual environment used in this study is just a simple virtual building with 9 rooms that has the rectangular shape and with the same length. And in some of the rooms, there are 2 to 3 everyday objects that serve as landmarks for participants to memorize their spatial relationships. And the movement in the virtual environment was driven by an elevator, which can move either vertically or horizontally. And during the learning phase, the participants watched a video of the moving through of this building. So all the movement is not controlled by the users, but rather predefined in the game engine that we used to develop this environment. Next. And during the learning phase, half of the participants experienced the exploration of the building with the regular shape, meaning that all the buildings have exactly the same length and shape. But the other half explored the building with the irregular shape, meaning that the lengths of some of the rooms was just half as the length of the rooms experienced in the regular condition. And the reason that we have this setup is to investigate to what extent the participants were sensitive about the irregularity of the geometric features of the building's layout. And for participants who experienced the irregular shaped building, half of them were informed about the irregularity of the building's shape in advance by providing them with a picture taken outside of the irregular shaped building, which was exactly the same as the figure shown on the right side of this slide. Next, please. No, this one, yeah. So, and afterwards, participants were instructed to draw a sketch map of the building's layout, as well as the spatial relations of the landmarks inside the building, along both the vertical and the horizontal directions. And we have developed a metrics to quantify the quality of the sketch maps, which I will not mention here because of the time limits, but I will just go directly into the results section. Next, please. Okay, so generally speaking, participants performed pretty well in the recall of the location and the name of the landmarks. So location here refers to the general location, for example, which landmark belongs to which floor. But some of the participants struggled with associating the landmark's location to the corresponding room that the landmark is supposed to be located at. So participants had some difficulty memorizing the exact location of some of the landmarks. And looking into the next, please. And looking into the individual's sketch maps, we noticed some kind of disconnection between rooms. And this is particularly the case along the vertical direction, as you can see on the right figure. So this leads us to assume or believe that both the visibility and the exploration mode matter in spatial learning for such architectural environments. And next, please. Okay, I'll go back to, sorry, go back. Yeah, thank you. So the reason is that in architectural environments, the visibility from a single viewpoint is very limited due to the room walls, right? So basically the whole environment is divided into different rooms. And this might have impeded the participants from developing an integrated mental representation of the whole building. And also during the learning phase, the participants were asked to move horizontally because they need to finish the exploration of all different rooms on the same floor before moving to the next one, which was controlled by the elevator. And this might be the reason that the disconnectivity along the vertical direction is more obvious than along the horizontal direction. Next, please. So for the future design of the VR applications, it might be useful to grant the users with some kind of like X-ray vision so that they can see through the walls of the rooms as a way to increase the visibility from single viewpoints. And it might also be useful to provide a guidance to guide their exploration during the building learning or building review, so that the different pieces of spatial information collected from separate viewpoints can be organized in a more structured and logical manner. Next, please. And another interesting finding we have is that for participants who explored the irregular shaped building, the vast majority of them tended to ignore the irregularity. So they just depicted the different rooms with exactly the same length. And this result is in line with the previous studies performed by Higati, I believe. So who suggested that human users or human individuals tended to regularize the irregular geometric features of the spatial layout as a way to save their cognitive resources. So next, please. So the implication is that in our future design of VR design tools, it would be helpful to find a mechanism which could be like a visual or auditory guidance to highlight the important, subtle features And in this case, in the building environment, actually this kind of bias in spatial memories could have huge influence on their efficiency toward the wayfinding to the destination, because everything is so condensed in such a highly structured environment. So in addition to providing some assistance, it might also be useful to find a way to detect the existence and development of the bias in spatial memory toward the regularization of the spatial layout. And in the case of immersive technologies, we could collect the user-generated data, such as their behavior and biometric data, and use some kind of machine learning methods to synthesize the data in order to detect the existence of the bias in their cognitive processing of spatial information. Next, please. Okay, so that's the first part. So I also would like to briefly talk about some of the interesting aspects we come across during the user evaluation with the PrismArch prototype. And the first is the movement in virtual space. So leveraging the real-time positional tracking system, the users with many modern VR headset now can just freely move around or walk around in the virtual space using their feet. And this is a very interesting aspect of VR, because it is the involvement of the embodied body-based cues in the interaction with virtual content, right? But in reality, it is very challenging to create a VR application that can match the size of the virtual space with the size of the physical play area that allows someone to play the VR game. And this is particularly the case in architectural design, because the design target sometimes could be a building or some regions in the urban area, which is often much larger than the play area offered by the VR game in real world. So next, please. So consequently, researchers and developers have come up with a colorful array of solutions for locomotion in VR that has the involvement of the body-based cues to some extent. And in PrismArch, we have two different locomotion methods. The first is the joystick locomotion. Basically, the user press a button on the controller to continuously move within the virtual environment. And the second one is the teleportation. So teleportation, by its name, is the jump of the user from one location to the other by enabling a laser emitted from the controller to achieve the selection of the next location, with infinite possibility during the transition process. And in these two methods, joystick locomotion and teleportation, are very popular and have been used in many VR applications nowadays. But the biggest problem is that there is a lack of involvement of the body-based cues, which might have lead serious motion sickness, which actually has been reported by some of our evaluators in the evaluation with the PrismArch prototype. So the open question is there a preferred locomotion method that can be used in the context of architectural design, such as the movement in the building environments or some highly structured urban environments, such as the metropolitan area? Or should we look into the individual differences and tailor the locomotion method based on individuals' preferences? This is an open question, and a lot of research needs to be done in this area. Next, please. And second is the design of the information display. And the PrismArch used the first two types of information display, the world stabilized and hand stabilized. So world stabilized means that the information window is fixed in the surrounding of the user, and its location is fixed and is independent of the user's movement. So ideally, it is possible to activate multiple word stabilized information displays surrounding the user and associate their locations with the locations of the virtual object distributed in the space, so that it is possible to create a semantically rich information display in the virtual environment with the capacity to visualize a large amount of information by the meantime. And hand stabilized is simple. So basically, it's the for example the virtual tablet attached to the hand controllers. So it's good for users to quickly access some tools or functions that they need to use frequently, which is like serving as a shortcut as the desktop application. And the third one, head stabilized, has not been implemented in PrismArch, but we think it could be useful for the display of warning message or some kind of information that requires the user's immediate attention. But one thing we should notice is that we should carefully design, like control adjust the size of the display window, because the head stabilized information display will always sit in front of the user's field of view. So we should just carefully control the size to make sure that all the information falls within the user's field of view. Otherwise, some of the information outside the field will become unreadable. So there must be a lot more types of information display that can be implemented in virtual environments. But the bottom line is that in the context of architectural design and planning and practice, there's a necessity to visualize a huge amount of information to the users. So how to organize these different kinds of information in a meaningful and logical and structured way is an open question. Next, please. Okay, the last one is last but not least, is the manipulation of the building models in VR. So which is essential and can be regarded as a core requirement for the design tools or softwares, right? Because in practice, the domain experts and architects might want to quickly prototype something and review the design, review and improve the design with their colleagues. So it is essential to afford users the capacity to quickly modeling something in the environment. And in PrismArch, we used some kind of explicit user interface to allow the manipulation of the models. So the way it works is that we attach a menu in the control to the controller with a slider showing the value of a specific dimension of the model. For example, the x-axis, the length along the x-axis of the size. And the advantage of this method is that the users can precisely adjust the dimensions or transformation of the model, because they can have access to the numeric value of each dimension of the model. But the drawback is that in order to manipulate a specific dimension of the model, they have to push the thumbstick, in this case, a lot of times in order to arrive in the adjustment for the specific dimension of the model, which is a little bit cumbersome and could be cognitive overwhelming for those users who are not quite familiar with the UI design in VR. Next, please. And alternatively, the way to is supposed to be a GIF. Okay, thanks. So yeah, I will go to that video, not this one. Oh, this one. Okay, so there's a advertisement. Sorry for that. Okay, so alternatively, there's no audio, always. So alternatively, we can use the embodied gestures to perform the model manipulation. And from my perspective, I think this is a more suitable approach in virtual reality, because it makes good use of the unique features of immersive technologies. That is the involvement of the body-based cues in the interaction with the model. So it can be very intuitive, so that the users do not have to memorize which button needs to be pressed in order to realize a certain type of interaction. But the limitation is also obvious. So compared to the PrismArch type of model manipulation, in this case, the users do not have access to the exact value of the specific dimensions of the model, so that they literally have to rely on their body as a reference to perceive the size or the orientation of the design target. And in some cases of the architectural planning, the lack of precision could be a big issue for some architects. But it really depends on the task. Yeah. So can we go back to the slides? Next, almost done. Next one. Okay, so yeah, that's all the of my presentation. So I would be very much looking forward to discussing some of the aspects I mentioned with you later on in the webinar. But yeah, please let me know if you have any immediate questions. You can just type in using the chat function of the Zoom, and later on we can discuss them. Thank you. So next one, I think the speaker is Christian Vater.
Thank you very much, Jiayan. Last but not least, I would like to present our empirical study that we did using the Rhino software, where we wanted to investigate the gaze behavior and performance of architects when interacting with an apartment model. And we were interested in how these navigation behaviors change when getting from their familiar environment, which is like the CAD software on the desktop environment, to a three-dimensional environment within a head-mounted display. And we were interested in investigating their cognition, but also their behavior. So getting to the experiment in more detail, we actually planned two experiments, the first with the desktop environment and the second within the HMD Vario VR3. And for the experiment, we had 10 different search tasks for our architects. So first of all, they had to imagine themselves being like a colleague of another architect. And their task would be to check the model that the colleague created in terms of clashes, in terms of errors. And so we created such ecologically valid tasks for them, namely to check, for example, if all rooms have doors, or if all doors have the same heights, etc. You can see that on the left. And on the right, you can see a top view of the apartment, which was shown to the architects and which they should inspect. And Martin was talking about this study beforehand in his evaluation phase, and we're going to go a little bit deeper into how this experiment was set up and on the results of this experiment. So, as I said, we had like the two conditions, one with the desktop and one with the head-mounted display, and I want to summarize just the desktop experiment right here, but just to give you an idea on what participants perceived within the desktop version and the HMD version, I'm going to show you on the next slide a little video on both situations. And in both situations, the task is to identify if the doors have the same heights. And on the right, I was trying to mimic the same strategy as an architect did on the left. And what you can see is that the navigation, the gaze behavior, and also the performance efficiency is much different when working in a virtual reality environment. So first of all, on both sides, the doors have to be selected or can be selected. There are different strategies. And then the doors can be isolated to kind of reduce the amount of distraction that we have through the rest of the model. And on the left, as you can see, there are very much familiar with their environment. They use certain commands to kind of isolate the doors, and then they only highlight the doors, and then they can quickly see that there's a door that is smaller than the others, and then report that back. On the right, you can see that this is not exactly the same way possible, because we first have to also select the doors and then like elevate, for example, the doors from the rest of the model. And then we can also see that one door is smaller than the rest. And since these strategies presumably are different to do the tasks we gave them, we wanted to investigate how performance changes within the different environments. And for that, we measured certain objective, but also subjective measures. For the objective measures, we looked at task accuracy. So how many of the 10 different features that we manipulated could be identified by the architects. We looked at navigation efficiency. So how much time did it take them to identify the incorrect features? We looked at navigation behavior. Specifically, we looked at the camera movements. So how big is the amplitude of moving the camera around the model to inspect it and search for different features? And to complement that, we looked at the gaze behavior. So especially at the viewing times on the different viewports, as you could have seen in the previous screenshot, they have 4 viewports, which is basically a top view where you can see the apartment from the top, a perspective view, which is mostly like the view we have in the VR situation. So where we can panel through the model in a first-person perspective. And the other 2 viewports are one from the right and one from the front. So you can have like different perspectives onto the same information, which is basically not possible, at least not in the version we used for the HMD condition. There you just have one viewport. But we were first interested in how often they use the different viewports when they have to solve the tasks we gave them. For subjective measures, we were interested in investigating the cognitive load, because comparing that between the 2 conditions is pretty important, because if cognitive load is already high within the Rhino environment, then we can expect that cognitive load must be even higher in an unfamiliar environment. We also collected some subjective reports and observations, and Martin already pointed out some of them. And we looked at the sketch maps. Similar to Jiayan's work, we were interested in the mental representations of the architects after working on the apartment model. And again, we were now interested in differences of those mental representations when working in a familiar and an unfamiliar environment. So getting to the results, here on the left, you can see the 10 different tasks. And in the second column, you can see the navigation efficiency, which ranged between 64 seconds and 193 seconds. So a big difference between the different tasks, which has something to do with the complexity of the search tasks. Because as I showed in the video example, investigating or searching if the doors have the same heights, you need to isolate them and then figure out which door is smaller than the other, and that takes more time. We can also see that the task difficulty, so they rate the task difficulty on a scale from 1 to 5, was highest for checking if all rooms have doors, because they had to move through the doors probably first to inspect the whole building. And it was easiest for them to check if all doors open in the right direction, for example. We can also see some variation in the task accuracy. Some tasks have been more difficult than others. When looking at the exploration behavior, so here we can see the camera movements in centimeter per second. For the 10 different tasks, we find no significant difference between the different tasks. However, the camera movement itself with 63 centimeters per second is a lot. So we need to always update our mental representations when moving around in the virtual building. And this probably causes a lot of cognitive load, a measure which I will talk about later. The next results I want to show you is the viewport selection. So how often did they interact with one of the 4 viewports in the different tasks? And on the left, you can see the results for all tasks averaged over all participants, and the individual dots are the individual participants. So as you can see, quite some variation here. But on average, the perspective and the top viewport are used most. So a use is characterized as clicking on the viewport and then zooming and paneling within that viewport. And once they select another viewport, the time is summarized over here and then averaged over the participants. And so as one take-home message here would be that architects seem to need at least 2 viewports to inspect objects from different perspectives and gather information from, for example, the doors. If we look at the tasks more specifically on the right, I know this is a lot of data, so bear with me for a moment, I explain that to you. What I want to show here is that the viewport selection also depends on the task characteristics. And the architects seem to strategically use the different viewports to inspect the model. For example, in task 2, they seem to make use of all 4 viewports to inspect the model. Whereas in task 5, for example, they mostly use the top viewport and not so much the other viewports. And in task 9, for example, they used more the perspective than all the other viewports. So there is a strategic use of the viewports to be efficient and search for the incorrect features within the apartment model. We're now getting from the navigation behavior to the gaze behavior. We can see that there's a similar pattern. The viewing times, which is how often does the gaze position overlap with the different viewports, shows that they mostly look at the perspective and the top viewport and not so much at the front and the right viewport. The other category summarizes all gaze positions on the menus. So whenever a gaze is switched to a menu or when they type in certain commands in the command line, this is summarized as other. And what you can see here is that gathering information by looking at different information is more important than using, or more time is spent on looking at different information than interacting with the Rhino software. Another way to look at the gaze behavior is to look at how often do they switch perspectives. Similar to what I just showed with the mouse and keyboard interactions, we can also transition with our gaze to the different viewports. And what is most astonishing here is that they switch gaze between viewports almost every 4 seconds, which is a lot, given that they have like a 20-minute exploration time. So on average, they switch gaze between viewports every 4 seconds. And the question is, how can we deal with that in a virtual environment where we have only 1 viewport? What is different? What is a different strategy here to compensate for the inability to switch perspectives? Or do we allow them to have a different perspective? And then it becomes a question how we implement that in our virtual reality software. On the right, the data is shown in a different way. It shows the transition probabilities, which means that how likely is it that I switch my gaze, for example, from the perspective viewport to the top viewport. And what you can see here is that the probabilities are very high from switching from the top to the perspective viewport, which indicates what Martin was suggesting beforehand, that by just looking at the top of the apartment, I may not be able to identify the right information from the right perspective. So I need to go into the perspective mode and then panel through the apartment on a one-on-one scale. I introduced also the mental representations here. On the left, you can see 2 examples, a good representation of the apartment and a rather poor representation of the apartment. Of course, we have to always question, is it the mental representation that is poor, or is it the inability of an architect to draw an apartment correctly? I would rather assume the first, because they're used to drawing such also complex models. But anyhow, depending on the expertise of drawing, and especially when getting to a 3D drawing, we have to take that into account when analyzing and interpreting the results here. On the right, what I show you is the accuracy of the mental representations. And here we had 4 different scales which we used. We first looked at if the rooms exist in the sketches. Then we looked at if the room connectors are correct. So if the rooms are correctly arranged so that one can walk from one to the other room. We looked at the room dimensions. So are the size and proportion of the rooms correct? And if the room names were correct. And what we can see here is that most of the participants were able to draw all the rooms correctly, but that the more detailed information rather get lost within the mental representations, which is an interesting finding which we want to follow up later on. Last but not least, last result here is the cognitive load. We used the NASA TLX to investigate cognitive load within their familiar environment. And what you can see here is that for the different scales, we already have medium to high cognitive loads. So we can expect that this is even higher in the virtual environment when using the HMD and not being able to inspect the building as one usually does. So we have to be careful by overloading participants in a new environment in the virtual reality. So summing up the results from this experimental study that we did, we have a large variability in almost all of our measures. What is similar through the tasks is the camera movements. And some of the participants already used like large views of one single viewport. They're not using all the 4 viewports, but rather preferred to switch to one viewport in a full screen mode, which you can see on the right image here. And this is more similar to what we will later have in our head-mounted display. And we will then see if those participants are better able to navigate and search for incorrect features within the head-mounted display. So what we found for the viewport selection, it seems that it's important to have at least 2 viewports to inspect information from different perspectives. And in terms of the mental representations, we can see that there's also a large variability across participants, but that the mental representations are overall good. And depending on which detail of information we are requesting, it becomes more and more difficult to remember all of the details. And now it becomes interesting to see all of these measures within the head-mount display and how these measures change in an unfamiliar environment for architects. And we believe that we can have some interesting drawbacks here or some interesting insights here from architects when interacting with the model within our head-mounted display. And with this, I want to give the word back to Christoph.
Christian, thank you. So let me just summarize very quickly. We've had a quite long session now with 5 distinct sections that represent the various contributions that our team has made to the PrismArch consortium. I hope you did find that to be of interest. And with this, I would like to go for one last slide. Where you see again our names and pointing to the 3 reports that we have generated within the PrismArch consortium that also give a slightly more formal background to what you heard about today. And this brings us then really to the final slide, I believe, which is an advertisement for joining on Monday for the last of the 4 PrismArch webinars, a session held by the industry partners about defining requirements of a collaborative environment for virtual reality. And I'm convinced that especially that session will very nicely complement what you've heard about today. And with this, I would like to close our webinar and thank you all for your attendance.
Thank you.
Are there any questions?
You can stop recording.